Okay, welcome to our last session of the day. Again, thank you guys for attending today. And this session is foundational science, setting the stage for success, specifically for the K2 grade band. So what we're going to talk about mostly in this session is just kind of our students' science education overall, and some of the non-content science stuff that we can focus on and do with our kids to really make them prepared to be scientists in the real world. So a little bit about myself. My name is Cassandra Armstrong. I'm a curriculum writer and professional development specialist at IMSA, just like all the other presenters today. My personal interests and kind of focus are on K-12 STEAM teaching and learning. So I was, before coming to IMSA, I was a high school science teacher, which might make you laugh since this is a K2 session. I taught biology, chemistry, earth science, physics, like everything. And the first thing I want to say is kudos to all of the elementary teachers out there, because I feel like there are two types of people in this world. People who can teach the youngins and people who can teach the old ones, and there's like no in between. So kudos. Like I said, I come from a background of high school, and I can't imagine teaching anyone but high schoolers like day to day in the classroom. But then, the elementary teachers are always like, I can't imagine not teaching littles versus the big kids. So it's kind of funny. But since coming to IMSA, I've really learned to love to zoom out and look at teaching science as a whole. So not just high school biology or, third grade science or kindergarten science. I like looking at the entire progression of science education, how it affects the teacher and the student from the beginning, preschool on up through post-secondary. So that's kind of my personal interests and kind of the origins of this presentation, if you will. So I gave the 6-8 version this morning in session 2, the 3-5 version in session 3, and here we are in session 5 with the K2 version. So we have a few objectives for the session. The first is we are going to examine the 3 dimensions of science as they apply to 3-dimensional learning within the next generation science standards. So these are our disciplinary core ideas, our science and engineering practices, and our cross-cutting concepts. We're going to look at the progression of those 3 dimensions as they build from kindergarten through 2nd grade. So, and even pre-K. So basically, this is like the most important part of our students' educational journey in science is, and in all subjects, kindergarten, preschool, 1st, 2nd grade, this is where they start. This is where they're not only learning, science, math, reading, all of those, but they're learning how to be a student. So they are getting habits ingrained in themselves about who they are as a student and trying to find that identity. And so that's something that we really want to focus on today, because we want our students to identify as risk takers and people who persevere and who are scientists. So and then we're going to kind of do a collaborative activity, 2 different collaborative activities where we're going to identify ways to provide early learners with these types of opportunities. So there's 2 resources that are basically the bulk of this presentation. The first is this textbook. It's probably a little blurry on there. A framework for K-12 science education. This is something that I use, I'm not going to say daily, but almost daily in my job, and even did as a teacher. This is the framework that the next generation science standards were built off of. There is so much valuable information in here. It's probably the first textbook that I have read cover to cover. Because it's really great. And a lot of what we're going to talk about today, I have pulled out of this book and put into kind of some more manageable PDF like handouts that you guys can access from the materials page. And then, of course, the Next Generation Science Standards, there's the website's nextgenscience.org. And that's where, you know, we have our performance expectations for students in science. So the beginning of the book, it literally might be like the intro to the entire book. It starts with this quote. And I feel like it's really meaningful because, again, like I said, one of my personal interests is to look at science education as a whole, K-12, you know, zoom out. And, you know, why do we do it? Why is science one of our main subjects that we teach, and why is it important, and all of those things? So the overarching goal of our framework for K-12 science education is to ensure that by the end of the 12th grade, all students have some appreciation of the beauty and wonder of science, because science is beautiful. Anyone who has watched a sunset can tell you that. Possess sufficient knowledge of science and engineering to engage in public discussions on related issues. So that kind of goes along with this next one, are careful consumers of scientific and technological information related to their everyday lives, are able to continue to learn about science outside of school, have skills to enter careers of their choice, including but not limited to careers in STEM. So if nothing else, I think the past couple of years of the COVID-19 pandemic have really shown kind of why some of these things are so important. Because as a society, we are not really showing that we possess that knowledge of science and engineering to be able to engage in public discussions on these scientific issues. We as a society are not being careful consumers of scientific and technological information. If you have any like social media, there is so much stuff that is shared that is pretending to be science, fake journal articles, fake news reports. You know, people are getting their information from random videos on YouTube and things like that. And that's not good, right? Because it's creating all sorts of these issues. And so I thought that was really interesting because, you know, a lot of times, again, for coming from a high school perspective, what do we want our students to get out of, you know, high school biology? Well, they should be able to make a diagram of the cell and label it, and they should be able to do X, Y, Z. Kindergarten, they should know like their seasons and weather and things like we always think about it in terms of content. But as an adult, you know, I became a science teacher. So yes, I did need to know those things. But my husband, who does nothing really to do with science in his career, has never, since the day he learned it in high school, needed to know the names of the organelles of the cells, or, you know, the elements of the periodic table. But so those aren't really what we need our students to walk away with. But those core practices of realizing that the organelles of a cell are pieces of a system, and that system works together to create the basic unit of life, and cells work together, and it's this big, you know, exponential scale of this makes up this, which makes up this, which makes up this. You know, that is a really good big idea for students to understand, that they can take with them into their adult lives. Or like the periodic table. The periodic table, yeah, it is a tool. It's a very important scientific tool. I don't really care if you have it memorized, because you can just Google periodic table, but do you know how to use it? Do you understand how it's arranged? Can you follow the patterns? Those kinds of things are what's important. So that's kind of our large scale end goal. Now, what are some of these guiding principles? And this was the version of this presentation I'm most excited to give, because this is really where we can, this really is the foundation, right? Like this is called foundational science, and the foundation is kindergarten, preschool, those early grades where, like I said, your children are learning to be students. So the guiding principles behind why this theory of science education works is kind of founded these six principles. So the first is that children are born investigators. You guys know this more than anyone, because by the time students make it to, the middle grades, definitely middle school, high school, they have had the curiosity beaten out of them, with being told, that school is not a place to be curious, it's a place to be right or wrong. There are right answers, there are wrong answers. But if you've ever been in a preschool classroom or a kindergarten classroom, that curiosity, and they're not quite as afraid to fail yet. They will take risks, and they will speak their mind without embarrassment for the most part. I have a 2.5-year-old and a 5-month-old, and even my 5-month-old, it was nice up in Chicagoland a few days ago, and we went on a walk outside, and it was her first time going on a walk outside, not in her stroller. And she was just all over the place, like big eyes, looking at everything, because she's curious. All children are naturally curious, and we want to, instead of teaching them that there is right and wrong, we want to teach them to use that curiosity to drive their scientific thought process. The next bullet is that there is a focus on core ideas and practices, which is basically, yes, while I just said, we want to focus more on the skills and things like that, we do have all of this science out there that we have been teaching. It's what we all learned in school. That is true, good science. And we do want students to learn part of it. So we're not saying, don't teach the content, but we're going to really focus on kind of digging deep into certain content areas instead of learning, a tiny little bit about every single scientific idea there is. The next guiding principle is that understanding develops over time, which, like I said, K2, that's the first grade band. That is the first tier. This tier really is the foundation of learning science, because all of the ideas in both content and skill, all three dimensions, the base is learned in K2. And then they learn a little bit about all of these ideas in K2. And then in 3.5, they build on those base ideas. And then in 6.8, they build on that. And then in 9.12, they build on that. So if students come to get to 3rd, 4th, 5th grade and they haven't had science yet, which I know happens in some schools, because of the push for math and reading, they won't have that foundation. And at that point, will probably have lost a lot of their natural scientific instinct. So we really want to make sure that we're building that foundation so that they can, when they revisit those ideas, some of the ideas that we'll be talking about in the presentation in 3rd to 5th grade or middle school or high school, they will be able to link it back to a core memory from kindergarten through 2nd grade. Science and engineering require both knowledge and practice. So again, similar to the second bullet, it is really, they go hand in hand. Like when I remember thinking back to my science classes, it was a lot of vocabulary, fill in the blanks, things like that, which is all knowledge. but we didn't do a lot of the practice. Practice being a scientist, using tools, analyzing data. And I don't know if the ACT even happens anymore, but I took the ACT instead of the SAT. I don't even know which one they favor now. It goes back and forth. But the science section of the ACT was basically all data analysis and, being able to apply practice. It wasn't content questions. So it was really hard for a lot of people because what they were learning in the classroom was a lot of content. The last two are, I think, the most personalizable, if that makes sense. We want to connect to our students' interests and experiences. So there's so much good information in my framework book and in the Next Gen Science Standards. And could they have written just an entire base curriculum for every grade level, like in kindergarten, this is what you should do. Here's, unit 1, week 1, day 1. Yeah, they probably could have done that. You can probably buy it out there. I'm sure you can. But in your classroom, you're going to know what works best for your students. So, it's hard to implement like a full curriculum because it could be something, if a curriculum's written in Florida and a bunch of it talks about oceans and sea life, and you have a student in Montana who has never seen the ocean trying to do it, that you're going to lose them. So this kind of more vague idea of the performance expectations allow you to take them and cater them to your specific students. And we know personalizing our lessons, ideas, teaching to our students is important, but what I've realized in the past few years of doing this job, working with teachers, is that you also need to personalize it to yourself, because how I teach something is going to be probably very different than how you would teach it, than how the teacher down the hall will teach it, because teachers are people too. And I think sometimes everyone forgets that. But we are people too, with our own personalities, our own interests, our own experiences. And so what, just like there's no one size fits all for students and that kind of thing, there's no one size fits all lesson plan for teachers. Some teachers plan out their lessons like minute by minute. That's great. That's not my style. I'm much more of an off the cuff type person, but that's okay. So again, we need to connect our teaching to our students' interests and experiences, but also our own personal teaching styles. And then the last guiding principle in all of this is to promote equity. So if there were just one national science curriculum, it would be really difficult because it would have to be written without any materials, because you can't assume that any or all schools would have, certain materials. Now, if schools have materials, you want to be able to use them. So we need, they were written in this, I'm going to say vague. They're not vague, but in this kind of open-ended way, so that teachers can, again, personalize the lessons and the units and how they teach these performance expectations to their students, to their classroom, based on what they have available to them. So there's no, high technology required for anything, but if you have it, use it. Okay, so the 3 dimensions, like I mentioned before, we have our disciplinary core ideas, which is our content. That's our stuff. Our science and engineering practices, which is what scientists and engineers do on a day-to-day basis, kind of like an upgrade to your classic scientific method or engineering design process. And then we have cross-cutting concepts, which are themes that carry throughout all aspects of science, and a lot of times beyond as well. And we're going to focus today on the SEPs and the CCCs. So a closer look at the science and engineering practices, like I said, this is kind of like your upgrade to your classic scientific method or engineering design process. Anytime there's an and in these, that separates your science from your engineering. So asking questions for science, defining problems for engineering. Developing and using models is used in both, planning and carrying out investigations, both, analyzing and interpreting data, both, mathematics and computational thinking, both. My math teacher friends get mad at me because I always tell everyone that the only reason we learn math is so that we can do science better. Is constructing explanations in science and designing solutions in engineering. We always want to engage in argument from evidence. So a lot of people do CER, the claim evidence reasoning method, or I have English teacher friends who use CLAIM, CLEAR, which is claim, link, evidence. I don't remember them, but it's basically CER, but a step up. But we want students to be able to make a claim and defend that claim using evidence. And yes, this can be done at the kindergarten level, which we will look at here in a little bit. And then communicating information. There's so much great science out there, but if you make a great discovery and you don't communicate it, then no one knows about that discovery. The DCIs, again, are content-based that we're not going to focus on as much, but we have three main sciences: physical sciences, life sciences, earth and space sciences, and then we have a category for engineering and technology. Our cross-cutting concepts are like our themes. These can be seen throughout all sciences as well as beyond. Patterns. There are patterns in life science. There are patterns in physical science. There are patterns in earth science. There are also patterns in mathematics. There are also patterns in literacy and reading, in poems, and there are patterns throughout history. We can apply patterns to basically any content level. And that's the other beauty of elementary is, as students progress through school, we start siloing math from science, from reading, from history. And, students think, okay, now I'm in math class, now I'm in science class. Well, elementary is a beautiful place where you can do all of these things integratively. You can teach a science lesson and read an article to find more information about it and create a graph to represent your data. And you're doing, all of these different content areas in this one science project. So we will look at these a little closer in a bit, but first we are going to look at the science and engineering practices. So we're going to do a bit of a collaborative activity. So I've made a Jamboard and I'll send you the link in a second. If you've never done a Jamboard, it's kind of like an interactive whiteboard. And I'm going to ask you guys to use the sticky note function. So on each slide of the Jamboard, I have put one science and engineering practice, the goal of that for the K2 grade band for that practice, and then some bullet points that show what students is specifically expected of students in the K2 grade band. This is all of the things on the Jamboard are from this book, but again, I just kind of took them out and put them in a more kind of non-book style organized way. So you are going to, on each page, use sticky notes. You do not have to do, every color sticky note on every page. We're going to have about 10 minutes. So if you can just get, sticky notes on half of them or whatever, it's whatever comes to your mind. It's not really like super organized. You have to do every one. A green sticky note will represent, oh, I already do that in my class. We do this really cool activity where students have to track the weather and they're, implementing this. Cool, write about it, put it on a green sticky note and slap it on there. A blue sticky note would be if you notice a natural connection to a DCI or CCE, like, oh, well, students can't talk about the cell without making a model of it. Something like that. Pink sticky notes would be any kind of useful links or resources. Oh, I have a great article that about, asking questions in elementary school, or I use this website all the time. Stick it on there. And then orange would be anything else. So let me send the link to the Jamboard. Okay, so I just sent it in the chat. And you can kind of see what I'm talking about here. There are 8 different slides, so one for each of the SEPs. So the first slide is asking questions and defining problems. In grades K2, we want to, by the end of 2nd grade, progress to simple descriptive questions that can be tested. So that's big. There are lots of different types of questions in the world. Some can be tested and some cannot. And that's the difference between a scientific question and a non-scientific question. And do we expect a kindergartner to know the difference? No, but by the end of 2nd grade, they should probably have enough experience with questioning that they can tell the difference between the two. And so then there are 3 examples of what that might look like. Again, you can click through and just start wherever you want to add a sticky note. It's this kind of square button over here. You can pick the color: green for a lesson that you have done, blue for connections that you see, pink for resources, orange for other. And I will go ahead and give us maybe till like 2:15, like nearing 10 minutes. And let me pull this out so that you guys can see the key here, and we'll go ahead and I'll give you some time to work on that. Okay, so we can debrief on this one a little bit. So looking at what we have here, the first one is asking questions and defining problems. And I put this sticky on this mitten challenge because I wanted to remember to share with you all. Actually, I will just send it right now. Let me get to the chat. We have, some of you might be familiar. We had a grant a few years ago from ISB to write some model NGSS lessons from K through 5th grade. And so I'm going to share that link with you in the chat. And there's like, I don't know, 8 or 9 lessons per grade level. And it's not like a full curriculum or full units or anything like that. These are just some really solid lessons that have some good 3-dimensional science learning. And so the mitten challenge that I mentioned on that first asking questions and defining problems, students are just kind of asked, given a challenge. It's kind of a defining problem. You need to make a mitten. How are we going to make a mitten? What qualities do you want out of a mitten? And students might say things like, you want it to keep your hands warm. You don't want your hands to get wet from snow, things like that. And then they are given a number of fabrics to test, play with. They can they're given fabrics and some snow and some other materials that they can just play around with and test so that they can try to design a good mitten. And that is a kindergarten level experiment. So that's a really good example of asking questions as well as developing and using models. I see someone wrote loose parts and design challenges. Yeah, so any kind of model or prototype for a design challenge is going to be part of that, developing models. Awesome. Let's see. Does it I see snow shovel challenge for planning and carrying out investigations. Oh, for analyzing and interpreting data, observing a rotting pumpkin. I love that. Does anyone want to speak to any of their stickies? Just explain it a little further or anything like that? Okay, I won't push. But let's see. Okay, I see a fall leaf hunt. Yeah, maybe like graphing the leaves or organizing the leaves in a graphical way that way. Sorting works really well for qualitative versus quantitative data. You can sort objects and then ask questions about how many, or you can ask about qualities. Yeah, so good. It looks like we had some really solid thoughts there. So the next slide is, oh, Sarah said, what about taking time with snow, how long it will last under the sun if you expose it to the sun? Yeah, that'd be a great little investigation. Take, some like maybe a cup full of snow and put one in the shade, put one in the sun, maybe take one inside, and you can measure and see their melting speed, or you can even just observe what happens to the snow. There are so many things you can do in terms of the science and engineering practices with that kind of activity. Yeah, thanks, Sarah. That's awesome. So these are the progression guides that I was talking about earlier. So we just did our science and engineering practice activity, and that's the middle one here. And then next we're going to work on our cross-cutting concepts, which is the left example. There are also 4 different versions of the disciplinary core ideas: physical sciences, life sciences, earth and space sciences, and then engineering and technology application. So there are 6 handouts that you guys can have to download today. And you'll get to that by going to, on the IMSAtute page, for the session, you clicked join Zoom link. Under that was session materials. So in the session materials, these are all listed as downloads that you can look at. And the reason is, on the Jamboard, I only put the K2 bullet points, but you might want to know, maybe you have a student who is more advanced and they have mastered, asking questions, and you want to see kind of what are the 3-5 expectations, or, whatever. Sometimes it's just nice to be able to see that progression as a whole. And again, those are all straight from this book. Where you are happy, welcome to read about it in chapter form. So we're going to then do that activity kind of a second time, but this time looking at our cross-cutting concepts. Similar with the sticky notes, we're going to look at green sticky notes for science ideas. So like the first cross-cutting concept is patterns. If you do something with seasons or weather that examines patterns, that's a really good science lesson. Jot it on a green sticky note. Blue sticky notes would be non-science ideas. so I think I said this already, but elementary school students haven't been siloed yet. So there are so many opportunities to do some integrative work with these students. So a blue sticky note might be a really good like math or history or ELA activity that also looks at patterns. Pink, again, is useful links and resources, and orange is questions and concerns. Let me share the link in the chat. And I think this the cross-cutting concepts generally have less bullets, so it might be a little less intimidating. There are 7 slides and each slide only has a couple bullets. So let me send this in the chat. And then go ahead and we'll take like, I don't know, 5 to 10 minutes and do the same thing with the sticky notes that we did the first time around. So I will see you guys in a couple minutes. Okay, so we had a few minutes to look through these, and I know just like everything, it is a little harder to do this kind of collaborative activity virtually versus in person, where we could be having some more discussions about it and things, but hopefully the Jamboard is still kind of a useful experience. And I will say that in the download materials page on Digital Commons, there's a PDF version of this presentation and a link to view the actual presentation like on web form. And these the Jamboard pictures at the top here link to the Jamboards. I'll leave them open for a few days if you think of other ideas that you want to add, and then probably on Monday I will change them to view only. If you want to come back and be like, oh, I wonder if there was anything someone put about X, Y, or Z, and you just really want to come look, those links will stay live just as view only on come probably about Monday. So for cross-cutting concepts, again, we'll just debrief through this really quickly. For patterns, we could go on and on and on and on and on about patterns. There's so many ways to talk about patterns in science and outside of science. Weather is really great. Patterns with leaves, yes. Different patterns and like sorting there, right? Like which ones have different colors, how many different colors do you have, different types of leaves, yeah, the veins, their shapes, the types of edges. There's so much you can do there. The next one is cause and effect. Okay, so yeah, I see a couple like gravity-based, like egg drop type things. Yeah, what happens if cause and effect is like the most basic scientific experiment. If we do X, then Y will happen. So there's a ton of things, again, you can explore there. Buildings and bridges, what happens if you add weight, exactly. Scale, proportion, and quantity. Water beads are growing animals. So yeah, like we do some of that in our preschool little steamers curriculum. So we have like the dehydrated water beads that are very tiny, you put them in water, they grow, and you can get those growing animals that do the same thing. So that's, kind of comparing bigger, smaller, and also cause and effect. If we put this in the water, then it will grow. Sea animals and fish. Let's see, systems and system models. Yeah, ecosystems, plants. For kindergarten through 2nd grade, we want to think about these big tangible ideas that students can see. At small abstract ideas or very large abstract ideas are going to be really hard for our younger students. So we want to get things that they can look at, touch, experience, So those are some really great examples. Energy and matter, objects can break into small pieces or come into larger pieces. So Play-Doh, blocks, any kind of building material, because yeah, building materials can break down or be used to build up. Structure and function, I put the shovel design challenge that I had mentioned before. That's one of those lessons on that NGSS page that I sent in the chat. Again, students, similar to the mitten challenge, students they are given some loose parts and they have to test those loose parts and design a little model of a winter shovel. So, do you want it to be scoop versus flat? Do you want a flat edge or a ripply edge? Things like that. And really just directly relating to structure and function. Another great structure and function is silverware. Have students try to eat cereal with a fork instead of a knife or instead of a spoon. And you'll see, kind of how that goes. So good. Thank you all for participating in that. And like I said, it will be posted up for you as well. Or it is still posted up for you as well. So a sample performance expectation, to kind of wrap up. This is an example of a kindergarten one. Plan and conduct an investigation to compare the effects of different strengths or different directions of pushes and pulls on the motion of an object. So this is kind of specific, but also open enough to where you can kind of do this using any materials or any kind of way that you wish. And if you notice, it is, we have an SEP, a DCI, and a CCC in here. If you look at the performance expectations on the website, you can mouse over to access or to see what kind of is what. And so I've done that here. Plan and conduct an investigation to compare. So that's our science and engineering practice, planning and conducting investigations. The effects of, that's our CCC, cause and effect. Different strengths or different directions of pushes and pulls on the motion of an object. So that's our physical science forces in motion content. And then what this will look like on the Next Gen Science website is this. You can mouse over on the website and it'll kind of link. So that first section is planning and carrying out investigations. And then again, links back to the information in this book about some of those bullets that we just looked at together. So kind of to sum up some supplemental strategies for implementation. So, we kind of covered a lot here. How overall can you do this in your classroom? Well, the first one is to play. And yes, I told this even to the middle school section, and I would tell this if I had a high school group. Just because you're in an older grade doesn't mean you can't play. Children learn best when they're playing. Adults learn best when they're playing. When you're doing something you enjoy, you're learning best. So let students play, give them materials, give them the freedom to ask their own questions and design their own experiments, and things like that. And it will, the rest kind of will come naturally. The second thing is to use technology if you have it available. Now, technology is literally defined as anything that is not found in the natural world. So, a blade of grass isn't technology, but a pencil is technology because you can't go and pick a pencil off the pencil tree. It was man-made, and it's a piece of technology that we use in classrooms pretty much every day. But if you have like hand lenses, so if you're observing fall leaves and looking at trying to find the patterns in the different shapes, sizes, colors of leaves, if you have hand lenses or can go to the dollar store and get a couple of those like big magnifying pages and let students look at the leaves through those, that adds makes the experience for them so much richer to be able to use a tool to learn. And then again, that I said at the very beginning, it's okay to make mistakes. Our students are taught at such a young age, that it's bad